So to start with finding out the center of mass of some standard continuous mass systems, let us start with finding out the center of mass of a uniform straight rod. So as you can see here, there is a rod that we have drawn over here. A thin rod, a uniform rod, means its mass per unit length is the same. It's of constant thickness, same thickness throughout its length, kept at a certain position, and we are supposed to find out the position of the center of mass of this rod. That means at that one single point where we can assume all the mass of this rod to be concentrated. So we shall be using our basic formula to find out the center of mass of a uniform mass or continuous mass system. To do that, let us first take up a few things. Let's assume that this rod is kept along the x-axis. So the length of the rod is along the x-axis. The left end of the rod, let us take to be kept at x is equal to 0, the origin. So that perpendicular to this is the y-axis, like this. This is the y-axis. Understand that all the parts of the rod lie on the x-axis. So there is no y coordinate associated with them. Here we are assuming that this thickness of the rod that we have taken is quite small. It's not a big thickness. So almost the whole rod is kept along the x-axis itself. Now what we do is, we consider a small portion of this rod, let's say a small element, which is, let us say, at a distance x from the origin, from x is equal to 0 point. And let's say this element that we have drawn here has its thickness, this thickness itself is dx. Dx, understand, is a very small thickness, so small so that we can assume that all this mass that we are taking up here is kept at the position x itself. Because dx is very small, we can consider this to be a point particle placed at x. Now understand that this can be done because we have taken the thickness to be very small, infinitesimally small. Dx is a very small thickness, right? How does that help us mathematically? We shall see that very soon. Now how to find out the mass of this small element of the rod that we have taken? Understand that the mass m of the rod, capital M, is the total mass of the rod, which is distributed over a length L. So can we find out something that we can call as the linear mass density or mass per unit length of the rod? We denote it by the letter lambda. This is generally a standard notation that we use for denoting the linear mass density of any body which is kept on a line in one single dimension. So lambda, which we call as the mass per unit length, will give us the amount of mass contained in unit length of the rod. And now if we want to find out the mass of this element dx of the rod, we call this small mass as dm. The length dx will have a small mass dm, which will be nothing but the mass of the rod per unit length multiplied by the elemental length whose mass we are supposed to find out. So m by L into dx gives us the mass dm of the small portion of the rod. Now if we have to find out the center of mass of the rod, starting with the formula x coordinate of center of mass as integral of x dm divided by the total mass of the rod. This is the formula that we shall be using for the x coordinate of center of mass of a continuous mass system which is kept along the x-axis. Now for this, see that for this particular element that we have taken up here, we can assume that its whole position is at x itself. That's what I was talking about earlier. Though we have taken only the left end of this element at a distance x, understand that the right end of the element will be at a distance of x plus dx from the origin, right? But since dx is very small, we can assume that this whole element is kept at a position x itself. It won't make much of difference. So we can assume that this whole element is placed at x position, and into that the small mass of this element, which will now be m by L into dx. It is this term that we have to integrate, and we have to divide it by the total mass of the rod. Now we are doing an integration with respect to x, so we need to put the limits of x also. If we have to divide this whole rod into small elements, from which x value till which x value do we need to integrate or do we need to add up. So understand that the left end of the rod, this particular end, is at x is equal to 0, whereas the right end of the rod, this end, is at x is equal to L. So do you understand that when we integrate this function from x is equal to 0 to x is equal to L, that would mean that we have considered all the elements of the rod from x is equal to 0 to x is equal to L, and that will cover the whole rod together, right? So the limits of integration here will be 0 to L. So we just need to solve this now. See that m cancels out, m being a constant, the total mass of the rod cancels out in the numerator and the denominator, and capital L we can take it outside the integral because it is a constant. Inside the integral then we are left with x dx from 0 to L, which will be nothing but 1 by L times the integral of x dx will be x squared by 2, and now we put the limits over here 0 to L. When we put the limits, we will get L squared by 2 minus 0, right? One L will cancel out and the final answer that we will get will be L by 2, which is the x coordinate of the center of mass of this rod. This is the result that we are looking for. What does this tell us? It tells us that the center of mass of this rod lies at a distance of L by 2 from the point x is equal to 0. Understand that this distance, this point L at distance L by 2 is a point which lies right at the middle of the rod. Were we expecting this result as well? Do we understand that if the rod is uniformly, the mass is uniformly distributed over the rod, it is natural that its center of mass should lie in the middle of the rod, isn't it? So this, we were anticipating this result actually, and mathematics is giving us the same result. Now what about the y coordinate of center of mass? Do we understand that each element here has its own y coordinate 0? So if at all we try to find it out, if we try to find out the y coordinate of center of mass by using the formula 1 by capital M integral of y dm on the same lines as we found out the x coordinate, can we say here each element has its y coordinate 0? So we will get within the integral here itself we will get 1 by m integral of 0, which will be nothing but 0 itself. So the y coordinate of center of mass of this rod is 0. So if we have to write the coordinates of this point is the center of mass of the rod. How do we write the coordinates? Can we write the coordinates of center of mass RCM as L by 2 comma 0, the x coordinate comma the y coordinate, right? So this is how we generally denote the center of mass of any body in terms of its coordinates.